So welcome to our CCNP class. We're going to talk a little bit today about VRF, MPLS, and MPLS Layer 3 VPNs. Some of this will be review, especially on the VRF area, but it's good to go over it because we talked about it in CCNP ENCORE, but it's a good thing to have it again. So we're going to talk about VRF and VRF Lite, how MPLS works, what it's used for, and then we'll look a little bit at MPLS Layer 3 VPNs. So let's first off talk about VRF Lite. Now, virtual routing and forwarding is the ability literally to take a Cisco router and chop it up virtually into multiple different routing entities, so to speak. So imagine instead of having just a single router, they can provide a single routing table. We can create VRF instances that allow us to have on a single router 3 or 4 different routing tables that are completely separate from each other. So it's almost like doing a VLAN on the routers, but you're VLANing in its entire routing process. This was created to support MPLS, well, not just for MPLS, but it was needed for MPLS, because we're going to learn about how service providers started taking customers' traffic and tagging it and then moving it through the network. Well, to be able to do that, they needed a way to separate different customers' routing tables from one another, because customer A and customer B may both be using the 10 network. Well, there was no easy way to route those across a single router without them being set up with VRF. So with VRF, here we have an instance of a setup where we have 3 different networks completely with 10 network /24, 172.16.00/24, and 192.168.1.0/24. And we've created 3 VRF instances, the red, green, and blue. And those 3 shall never match, shall never meet. They are not going to exchange routes between one another as far as red, green, and blue themselves. Now within red, they will, okay, and within green and within blue, but it is really like taking the router and creating VLANs for routing on the router itself. So very useful for service providers because they're moving multiple client traffic across their networks, and they need a way to make sure those are completely separate from one another and won't impact one another in any way from a security standpoint. You even have the ability to, in this case, you see here, this is how to create a VRF instance. So IPVRF red, exit IPV, and you wouldn't have to exit. You could just type IPVRF green and create a new one. But this is creating red, green, and blue. And then when you do show IPVRF, you will see the different VRFs. Okay. And then you can place your interfaces into different VRFs. You also can take a single physical interface and place it into multiple VRFs by creating sub-interfaces. So the sub-interface can be in a different VRF. So you don't have to have different physical interfaces to have multiple VRFs on a router. You can use sub-interfaces to do it. But once this is created and you apply your IP addresses and your routing, those VRF instances are not going to even know the others exist. Here's an example of doing VRF on sub-interfaces, okay? So here's red, green, and blue all on a single router instead of having multiple physical interfaces, all right? You then go ahead and put your IP addresses, you put your encapsulation for the, if you were doing it with a single interface, you would do it with the .1Q 100, 200, 300 if that was the particular VLAN we were going to use to do your .1Q tagging. And then if you do a show IP route, you'll see that by default, once you create the VRF, you need to start putting in the route information. You've got a global routing table, but in this instance, we did not leave any of our interfaces in a global routing table. So by default, we have a global routing table, and you'll notice we see nothing because none of our interfaces were left in that global routing table. We moved everything into a VRF. So to see the VRF, you've got to do show IP route VRF and the VRF name, And when you do that, you will suddenly start seeing your VRF's output, okay? So here again is an instance of setting up VRF, okay? Configuring subinterfaces to VRF instances, IPVRF red, green, and blue. And notice you don't have to type exit. You can just type them in. They'll all be created. Then going in into the subinterfaces, putting in the information about the .1Q tagging. Let's go up here and look at 2. Hold on one second. Let's go up and look at 2. So this is where we're doing subinterfaces between R1, R2, and between R2 and R3. But those are agreed upon. We've already agreed upon our subinterfaces and what we're going to tag them as for our inter VLAN routing. Okay. In this case, our VRF routes. Okay. So here is show IP route VRF red. We see the red routes, which are the 10 routes. Show IP VRF green shows our 172.16 routes, and show IP VRF blue shows you our 192.168.12 routes, or 192.168.00/24 routes. Notice that without the VRF, there was nothing showing because we did not leave any interfaces in the VRF, in the default route table. Okay. Here again is R3 configuring its communication to R2. And then again, you look at show IP VRF instances. We'll show you your instances and the addresses associated with those. And that is literally creating VRF instances. So it's not difficult to do. Now that traffic will be completely separate from each other. And you can even run different routing protocols on each one. Red could be running EIGRP, blue could be running OSPF, and you could be running RIP on green if you were crazy. Okay, but you could do it. Now here's an example of using using EIGRP and the VRF. So router EIGRP VRF example, put a family name VRF red in autonomous system 10. All right, and then what networks we're going to route in that VRF. Then we have an address family IPv4, and we're going to do the autonomous system 172 and then 192. So we have basically turned on routing for each one of our VRFs. In this case, all of them are running EIGRP. You don't have to do that. They could be running separate protocols. But none of these will share routes between one another, and none of the updates will go between these different VRFs. So show IP EIGRP VRF red instances. Notice you basically just put VRF and the name into the command to make a command into a VRF show command, and it will show you the interfaces that are in it and then the information that you are looking for about that particular interface. Any questions about VRF? Pretty simple, pretty neat. Nicholas, are you running any VRF stuff in your environment there on campus? I know you don't have a microphone, but I'm trying to think if we've got any on our network here. I don't think we have any VRFs on our network. Typically, what I've seen is with VRF, and it's used with the support MPLS in the core of a provider network more than anything else. Here is an example. We're going to now talk about MPLS. Now let's think about multi-protocol label switching as a way for a service provider to support moving multi-vendor traffic through their network. It's designed to support a lot of different layer 3 protocols, but we only really in the real world today, we only use IP, v4, v6. But what you end up with is a multi-protocol enabled routers set up what are called labels. So you create a label for a network. And then inside of the router itself, when you turn on MPLS, they can exchange labels to route table matches. So you end up with an IP forwarding table, just like you do a normal routing table, but you also end up with a label forwarding table, which is if a packet comes in that is destined for this network, it goes to this next device in the line with an MPLS. It is honestly very similar to tagging VLANs, except we're tagging networks to tell them where to go. Oh, that's a good use there, Nicholas. Separating student labs where they had the same IPs to show its use. Yep. And that is true. Now, I wish our example actually didn't do what it did. Our example of VRF shows 3 different networks, 3 different complete network numbers. They could all 3 have the same network number. They could all be 10.0.0.0/24, and they would work just fine because those VRFs don't see each other, okay? So the label information base or label and the label forwarding base is set up so that anything coming in can be forwarded to the next path in line with labels. So when we end up looking at our networks, okay, we end up with edge LSR routers. Those are label switching routers. Edge routers are where labels are placed on the traffic and where they're removed. So when you deliver traffic from at an edge router, the MPLS labels are removed. And that is because the MPLS label wouldn't make sense outside of an MPLS network, just like a .1Q frame tag makes no sense outside of a link designed to support tagging. Same thing with these MPLS labels. So in this case, we've got intermediate LSRs, and each one of those are going to be programmed with a series of information so that they can create a label forwarding base to know where to send traffic. Now, this label switched path is a cumulative path or sequence of routers that are set up in the MPLS domain. It is a unidirectional path. It is possible that the source to destination could be different than the return traffic, although that normally we would try to use the same traffic, but because that's just normal. And also typically these paths are built by looking at the forwarding information base and then building from that your label information base. You'll see that in the case of going from 192.168.0.0 to the 10 network, there has been a label path built that goes using labels 87, 11, 63, and 23 to get it all the way over to the destination. Now, this would have been programmed into the routers via MPLS by the service provider, okay? So it adds that label into the packet so that there's a label inside this layer 3 packet. That label tells it where the networks are located. So it says here, you come into edge router 1, it says to get to network 10, all right, you label 10, get network 10, go over to 87. Then say, all right, to get network 10, go to 11. To get network 10, go to 65. Network 10, go to 23. And then this edge router is already connected to the network, so it knows to send it directly to it. Now, you can locally configure this, or you also can have propagation through routing information protocols. You must have reachability here. Notice none of this is a routing protocol. None of this is saying how the IP address is built out here. There's still a protocol running, and reachability has to be available for these to be able to get to one another. But MPLS, using the MPLS forwarding table and the IP forwarding table, determines how to get to the next hop for the label. Now, I've never configured this on a router in a service provider. It's one of the things I would like to do, but one of the things that's nice is once you set up MPLS, they actually can use a protocol called label distribution protocol. So when you set the label locally, it will then send it out via multicast to one another, and they will build their own label information base. So you can set it with your labeling locally configured, and then use LDP, label distribution protocol, to allow it to send that information to each other. So this will tell it here, hey, R11 can get to the 10 network by 19, R2 can get to it via 87, and so on and so forth. So all these exchange their MPLS information, labels, and then they're able to get all the way from 192.168, the path, to 10.0.0.0. And this ensures that for this particular customer who is running a 192.168 network and a 10 network, their traffic will follow this path and it is not going to be touched by any other vendor's traffic or any other customer's traffic in this network. So pretty neat. Again, developed mainly so that vendors can take one infrastructure, one set of routers in their core, and move traffic from multiple different customers and keep that traffic separate from one another so that it won't interfere with one another. Because they may have 5 customers that use 192.168.0.0 and 10.0.0.0. And to keep that all in check, they use MPLS to make sure those two don't even see each other. Now, MPLS can also be used to do VPNs. Okay, so you can use MPLS to create what's called a P domain here. So MPLS domain is the P network, customer sites are the C network. So this P domain connects the customer sites, so you can create a VPN across the MPLS. This would allow it to not see those hops in the middle. So we're able to look at this. The customer edge routers connect to the PE router edge in the MPLS domain. The PE routers 1, 2, 3, and 4, and 5 are intermediate label switching routers in the MPLS domain. But as far as the customer sees, they think that they are connected directly to one another. Okay. You don't have to worry about overlapping address spaces. You don't have to worry about any of that, because this also adds a layer of security, because the traffic, when you do these VPNs, you would encrypt it. So you've got encryption of your traffic. Up here, the traffic's not encrypted. It's all separate because it's all got different labels on it, but we then can add an extra layer with using encryption. Plus, this can keep from having issues if there's a reachability issue or something of that nature. So ingress, egress. The goal in this is to have site 1 and site 2 to exchange the routing information and not see all these hops in the middle. It's also for security, to help with security. But you'll still have to have, you'll notice here, to support this, they'll have to have different VRF instances. So each one of these routers will have a VRF instance for customer A and customer B. And then the C customer router and the PE router will exchange IPv4 routes using some type of protocol, whatever that happens to be. And then those are putting the customer specific VRF on the table. The customer sees the P as another router in his network, but it is not, you don't see any of the internal routers. They're all hidden. So what ends up with the customer here is this customer router has a complete VPN across from CU1 to R2. Now this can also be used with BGP. The PE routers can learn from routes from CE routers, and they can redistribute that into multi-protocol BGP. The P routers don't participate in the BGP, only the PE routers. So they're forming what's called multi-protocol internal BGP neighbor relationships with each other. They also still have to have some type of interior gateway protocol to pull information off of. Now this, let's see, try I got this right, because this one confused me. If all the routes are being put into the MPVPN, that was previous one. Route distinguisher. Okay. So VPN 4 routes. Let me see if I understand this correctly. Okay, so the CE and the PE router, these customer router and the provider edge router, exchange routes using the dynamic protocol. The PE router places the customer specific routes in that customer specific VRF table, which makes sense. The routes in the customer's VRF table are redistributed into multi-protocol BGP as VPN-V4 routes. And then the PE routers exchange those VPN port routes over multi-protocol IBGP, and then they redistribute that back into whatever routing protocol on the customer specific side. So basically, it's a way to move the customer's routes across the traffic or across the network here with multi-protocol BGP as the transport layer across the MPLS network. Okay. The big thing here, though, is the label stack. You've got a stack. 2 labels are required for the traffic to go through. It is the VPN label and the LDP, the link database label, and that will tell it basically the correct path to use across the MPLS network. And then we do label switching. So here's what we see here, what it does label switching. And these labels will be exchanged via the label LDP protocol. So we exchange these labels between all of our devices in the path, and it creates, once again, a label path that is used for this traffic. And that label path is built using LDP and the information fed into it from other routing protocols. And with that, it's able to move across the provider network and be completely separate from the other customer's information. Now, that's pretty much MPLS. And so the topic was configuring VRF, signing the VRF, creating subinterfaces, verifying the routes, and then understanding the benefits of MPLS. Okay, so we don't have to learn how to configure MPLS. We need to understand how the benefits, and the benefit really is being able to utilize one set of equipment from your vendor to move from your service provider to move multiple companies or multiple different customers' traffic through the network without them affecting each other. You can see how much that's much more economical than having to have an entire setup for customer A, entire setup for customer B, so on and so forth. Have either of you ever actually configured MPLS? I have not, either not in a real world environment. I've done a little bit in a lab environment, but even that's a little difficult to do. All right, I'm not going to spend a lot of time on DMVPN, dynamic multipoint tunnels. It is basically a tunnel that where the endpoints can use a specialized protocol to figure out all the parts, what's called next hop resolution protocol. And by using DMVPN, you can lessen the configuration load on your VPNs. You don't have to do the long form configuration that's so common with a typical IPsec VPN or an IPsec tunnel. It allows them to build tunnels on a as needed basis with DMVPN. So you'll have a hub, and then all the other routers are spokes, and those spokes will initiate a persistent VPN to the hub router if needed, but also they can dynamically build spokes to other sites if they need to. So you don't have to set it up to where if you've got, let me see if I can find my picture in here that I need to talk about. Yeah, here's good. So let's imagine we've got all these. With DMVPN, by default, you set up a persistent connection back to the hub, but you don't have to set up connections between R2 and R3 and R3 and R4. If R3 needs to talk to R4 with DMVPN, it can create a dynamic multipoint VPN connection from R3 to R4 by using the information from the hub and next hop reachability protocol to create that tunnel. And then when that tunnel's done, it just drops that tunnel and doesn't use it anymore. If we did not have DMVPN, we would literally have to build a tunnel between R2 and all the other devices, R3 and all the devices, and R4 and all the devices. But we don't have to do that. If the MPLS circuit dies, they're to be able to pay for a flat rate egress measure back to the home site. Okay. And so that in that case, Nicholas, the MPLS circuit was used to provide metering so they could charge it for it, correct? Is that what it was? Were they actually doing metering across it, or was it just to force all that traffic across that particular circuit? Okay, I got you. Okay. So basically it was saying, I understand, it was the opposite of what I was thinking. So they weren't sticking it in the tunnel to be able to meter it. They were sticking it in the tunnel to turn the meter off because that tunnel had a set cost, regardless of how much traffic went through it. Okay, that makes sense. You just create a VRF. That VRF is going to be that network that's not going to be metered. Set up an MPLS path. The MPLS path is all that traffic goes through that, and we don't care how much traffic goes through it. That particular path costs you X amount of money per month. That's a good use. I could see that. Okay. All right, everybody, I have graded everything up to this point. So everything should be graded. Everything should be ready to go. We've got about 2 weeks left in class. Many of you are close to being finished. I've got about 3 of you that are real close to being finished. So please keep working on that. If you have any questions for me, let me know. If there's any issues with the labs, let me know. Remember, our hands-on final lab is that lab inside of NetLabs. So by logging in here, and it's much easier than the CCNP ENCORE one. I've already had somebody complete it, so be aware of that. It's the lab in our course labeled SA1. So that's your hands-on final. And everyone, please do take note, on Wednesday of this week, we are going to take NetLabs down for about an hour from 1 p.m. to 2 p.m. Eastern time to do a critical update on our NetLabs server. So just be aware it is not going to be available. It should be back up, knock on wood, by 2 o'clock. So just want to throw that out there to you so that you'll know that we are going to have maintenance on April 17th from 1 o'clock to 2 o'clock. And I know it's not a great time, but honestly, we have people all over the world, so we just had to pick a time that would, one, we had availability for our data center and our data center lead. So, but that's what we're doing. Okay. All right, everybody, that's all I got today. I appreciate everyone. If you have any questions, let me know. If not, I will catch up with you next week. Thanks, everybody.
Stay safe.
You too, Clay. Be good.